I'll just record to the computer. All right. Are you guys able to see this pretty good? Do you need me to zoom in at all? All right, perfect. So what I had planned out for today was I was just gonna go over the basics of the main topics like DMA, recursion, linked list, queues and stacks. For algorithm analysis and Big O, I'll probably pull up some practice problems from foundations exam for that because I don't really know how to show this in code besides like loops and stuff and asking you guys to figure it out. Um, but if there's anything else you guys want me to cover, zoom in a bit. Yeah, yeah, for sure. That better for you? Perfect. Okay. So let's just start with DMA. So, with all of our assignments, we've been having to dynamically allocate memory for majority of our yeah, 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 definitely got to lock in DMA. So we know that we have three functions for DMA. We have malloc, calloc, and realloc. And then obviously free is associated with all those things. So for instance, like with malloc, let's just say I wanted to create a pointer, integer pointer, right? We know the syntax is malloc. And then usually this is just the AI throwing it in. I like to start with the size of, and remember you designate the data type that you're trying to set up in that array or struct or whatever. So for this, I have called it an integer array. So obviously the size has to be of int. And then the second argument would be how many of that do you want, right? So I'm just going to go ahead and go with 10, right? So if you struggle with DMA, this is not a constant. Oh, we're not in main. Whatever. Let's just do that. Okay. So if you struggle with DMA, just remember you have your malloc. Sometimes you'll see a typecast in the front. If you guys remember typecasting from intro to C, is basically where you can like override the type that you want for that malloc. We haven't really seen that in this class. You don't really have to worry about it so much, I would say. What you really want to focus on is just the simple malloc statement. So you want to have a malloc, the data type that you're creating inside of that malloc, and then how many of that data type that you want to create. Does that make sense to you guys? Okay. So we see this already. Dr. Ali covered it in class. It's standard practice that you want to make sure that your memory allocation was successful, right? Why do we want to make sure that it's successful? Because you want to avoid segmentation faults. In other words, if you allocate memory and let's say you have no memory in your heap at all, and then you just go straight to assigning values inside of a struct or inside of an array that you don't have permission or access to, you're gonna get seg faults, right? So we see here already, it's just a simple check, right? So you just want to check if whatever you created is set to null, right? Null essentially meaning like there's nothing or it doesn't exist, etc. Um, Normally, like you'll just do a printf statement, like memory allocation failed. Um, I lean towards more of this. I learned this in my intro to C class. I can, yeah, that's fine. I can. You'll see more of that when we go into linked list T. I'll show you the structs for linked lists and queues and stuff and how to allocate memory for that. Right. Um, this is just standard practice. You'll do like a print statement and then you usually just return. Um, for the exam, she did say that we don't have to worry about that. We can just jump straight into the solution. She did warn though, read the word problems correctly. If it tells you to check if the memory allocation was successful, this is what that means, right? That this is what they're telling you to check for. They basically want you to check if it's null. If it's null, then it failed. And then after the failure check, you can continue into your solution. All right. So just be careful when you're reading the word problems and you're making sure that you're delivering what they're asking for. So after that, we have an array of integers that are size 10, right? And you have to remember with malloc, inside of that array of size 10, it's just garbage values. So for instance, if I loop through this array right now and I printed each element at their indexes, we would get some random numbers. That's just how malloc works, right? If you wanted to initiate those values in the array to 0, for instance, that is where calloc comes in. Okay. So calloc is the function that we would use to dynamically allocate memory for structs, pointers, arrays, etc. If we want to have a like an initializer, so to speak, right? So we can do the same thing, right? So integer array 2 is equal to calloc, and here it goes again. 1 second, guys. I'm sorry. Addison. My apologies for that, guys. Okay. So with calloc, to my understanding, it's actually the size of what you're trying to designate first. So like int and then how many you want in there. So notice the difference. This in malloc, you're multiplying by it or you're adding by however you want. And calloc, you need your comma because it's two arguments, right? So you need your data type and then the number that you want, right? Or not specifically like the number you want. Like this won't initialize to 10, but you'll have 10 indices that are set to 0. Okay, does that make sense for you guys? Again, I can double check on that. Let me just make sure. I apologize. It's actually the opposite. So it's the number that you want, and then look at that, the AI was right, and then the data type. So there we go. So it's flipped, right? And then obviously you would just do your null check, make sure that the allocation was successful, and then you can continue on. Now, when it comes to realloc, we have our arrays, right? Um, we can say AIR equals realloc. So the first argument is going to be um, the array that you're passing in or whatever, dynamically allocated memory that you used. So we're passing in the array. Yes, this is. We're passing in the data type expected and then the new size that you want, right? So originally our array was of size 10. Now we're reallocating memory to size of 20, right? Important for realloc to remember is that it always saves the original data at their respective indexes. There we go. Right. And this is important when we start getting into the circular queues and the array approach. Okay, guys? Because and I'll cover this later, but just remember this. So when you realloc and you resize for more space, um, all of the elements and their indexes stay where they were originally in the array. The important thing to do when you do realloc, if you check if it's null, right? do you remember that Dr. Ali kind of touched on that today? If you have a realloc and it fails, you have to free that data or you'll have a dangling pointer, right? So you have to it's not just checking if it's null anymore. You have to manually just free it. So this is just basic DMA for you. Um, Going even further, let's say we have a double pointer, and then we're just going to loop through, and I'm not going to do the if check. This is kind of saying it already. So the way I was taught it, so for every pointer you have is a free that you need to do, right? So in this double pointer array, that means that we're going to have two frees. Okay. You're gonna have to loop through the array and free every pointer inside of the array. And then after you free that, you free the original double pointer. Okay. So we see that here. So we looped through the array and we freed every single pointer that we created here. Okay. So you could think of it as this. We have 5 rows and 10 columns, right? This is going to show me. Right. So if it was a triple pointer T, you would have to loop through it 3 times. Correct. So like you would go through like IJ, um yeah. So you'd have to do a double loop, and then after that you would just free the original on the outside of the loop. So as many pointers as you have is how many frees you will have. Okay. And this is the very bare bones to DMA. Um, let's say I know we had this on the quiz, and it's probably going to be like a question. Um, what happens if I try to do what happens if I try to do that? Anybody remember? All right, there we go. Right. So we have pointer equal to null. So it's just pointing to, basically nothing. We cannot just randomly assign it to point to 4. Right. You would get like a this is called like a dangling pointer almost. So you have to be careful with your pointers as you're doing it. So this is just a practice of DMA. Um, we'll cover recursion, but I feel like a lot of people are struggling with DMA. So we'll go into linked list, and that should give you a little bit more practice with DMA. How does that sound to you guys? Or if you want, we can jump right into recursion. Okay. Okay, perfect. So we know with linked list that we need to have structs, and everybody knows that, to create a struct, you have to have like a type def, struct, and then whatever you want to call it. Um, and then struct node next. And I'm just going to call it node. Right. Okay. So we know that a linked list, usually yes. From my understanding, Dr. Ali said that majority of the exam, not majority of it, but a good portion of it is going to be like fill in the blank, so to speak, or you know, kind of like the quizzes, like given this type def and this function definition, go ahead and fill out the rest of the function for us, etc. So we know that inside of this node, we have an integer data type and a struct pointer, right, to the next node. So let's go over and like list. Ooh, not here. Okay. I'm so sorry about that, guys. Okay. Um, so I'm not going to set it equal to null. So we know with linked list, we have to have I'm going to create a helper function. Ooh, okay. Sorry. So for structs, you have to dynamically allocate that memory for them. And so we notice that we have two things, right? We have data and then we have a pointer to the next node, right? So when we're creating a node, excuse me, we need to allocate the memory for it, right? So we have a new node. We're going to malloc it, and it's going to be the size of the struct itself. Okay, is that confusing for a few people? Does everybody feel comfortable with that? Okay. And then obviously we want to check if it's null. We want to make sure that the data allocation was successful. And if it fails, we're just going to return null because we're expecting a pointer to be returned from this function. And if it succeeds, we already see that since we're dealing with a pointer, the way to access members of a pointer is with the arrow operator. Yeah, we'll go through that. And then we're just going to return new node. So to explain what I did here is that we allocated the memory for the node. We checked if the allocation was successful. And then after we seen that it was successful, we assigned the value that we passed in to the data member of the struct. And then because this is a new node, we're setting the next pointer to null because we don't know where it's going to fall in the linked list. And then after we're done, we're just going to return that new node, right? So we have our helper function to create the node. Let's go ahead into a demo, right? And then I'll create other functions. and then void. And then what else did they say? Insert. You want to go over free? Okay. Um, we'll go ahead and do insert sorted. What else do we want to go over? Did they say just inserting anywhere in the linked list or like, oh, okay, perfect. So we'll go with, oh my gosh, I wish there was a way to like turn off the auto suggest. All right. So we know when we're traversing a list, we're going to start at the head pointer. And Dr. Ali showed us that we need to use a walker pointer. Do you guys know why we need to use a walker pointer to traverse a list and not using the head directly? I'm just asking you guys these questions so you understand like the concepts behind it. It's not to keep track of the position. So the head is, again, remember the head is our entrance into the list. Right, right, Nicole. So if we move the head, right? So remember with pointers, when we're passing in pointers into a function, that's passed by reference. You're not creating a copy of the linked list, you're directly dealing with the original linked list. So if you're moving ahead to go through the linked list, you lose access to all the previous nodes as you move through the list. That's why we need that helper to move through the list for us. That way we don't lose the entirety of the linked list. Do you guys understand that? Yeah, it's all good. It's all good. So I just want to make sure you guys understood that. That's why we use a helper function. That way you don't lose access and have a memory leak, so to speak, because we're just moving pointers and then losing the previous pointers before without freeing them. That's why we have the helper pointer to move for us, right? So if we want to traverse the list, we can say node pointer temp, and we can set it equal to head. What this is doing, guys, is that I wish I had like a drawing. um, essentially, we have the pointer that points to head. All we're doing is creating a second pointer to head. We're not allocating any more memory. We're not creating a new node or anything like that. We're just having a pointer point to where the head is currently at, right? And we can say that while it's not null, right? So there's something at temp. This is just saying while temp has something inside of it, we can print what's inside of it. We know that it's an integer inside of it. Um, excuse me. And then we can move our walker to the next node, right? Okay. So this is how you would traverse a singly linked list or even a doubly linked list if you're traversing forward, right? So we have our walker that we created. We pointed it at the head, our entrance into the linked list. We check if there is something at temp, like it actually does exist. If it does exist, then while it does exist, we'll print out what's inside of it. And then after we print it out, we just move on to the next node until our a while loop conditional fails out. And once we know that it fails out, we have completed our linked list. That makes sense for you guys? Wouldn't you want temp next equal to null is while conditional? Oh, not equal to null. I'm sorry. Um, you can do either or, right? So if you do, actually, you can't. I'll tell you why. So Levi, if I did temp next not equal to null, right? Let's say we get to actually I'll do it right here. Let's say that this is our list. Right. Exactly. So you would hit 5, you would see that the next pointer is null, and you would stop basically at 3. So you would essentially go all the way through the list, right? So we see that something does exist at 5, we print it out, we hit the end of the list. All right, that's obviously null. We don't print anything out, we end the loop. That makes sense to you, Levi? Perfect. Did you need me to repeat that again, Tony? Okay, perfect. So again, with majority of our linked list functions, you're going to be passing in the head, right? The head is the first node of the list. It's our entrance into the linked list. The reason why we create this walker pointer is because if we move the head itself, we lose access to the members of the linked list as we traverse it, right? So instead of like temp being null, if I said this, let me comment this out. If I did this, you see this reassignment right here, head equals head next. I'm constantly losing access to all the previous nodes of head. And then if I wanted to use head again, like if this was my original list right here, and I went through this traverse list and I'm constantly moving the head, right? So we start at 1. Okay, head is not null. Perfect. We print out 1. We're moving head to 3. 3 exists. All right, we're printing out 3. We're moving the head to 5. 5 exists. All right, we print it out. We're moving the head to null. Oh, wait, we can't print that out. We're out of the traverse list function. If I do something else with that linked list, like let's say if I wanted to print out the first node of my linked list, I would get essentially null, right? Because why? I moved my head. I no longer have access to those previous members of the linked list. That makes sense to you, Tony? Perfect. Okay. Okay. All right. So insert sorted. So there's a couple of base checks that you want to do. What do you guys think is the first check? If this thing wasn't, my goodness, what do you think the first check would be if you're trying to insert a node into a linked list? Right. Exactly. So if there's nothing inside of the linked list, then we obviously know that our new node that we're trying to add in is going to be the head and it's going to be the tail, and we're just going to have to move the next pointer. Well, we just have to assign it, right? We'll see. So if the list is empty, right? So if head is equal to null, then we know that head is equal to create node value, right? We already remember in our create node function, we set next equal to null and we return the node. So this will return our new pointer and we're good, right? Well, again, I hate this auto typing thing. What do you think the next check would be? So we checked if it's empty. What's the next check? Again, this is insert sorted. And let's say it's in ascending order. And for those who don't know, ascending is like Zero, one, two, three, four, five. That's ascending. Not head next, right? So we already checked if head is equal to null. It doesn't matter if head next is null. Okay, the value compared to the others, right? But there's a very specific check. What if our head is the value 4, but our new node has a value of 2? What do we do then? Would it be the same as inserting anywhere else in the list? It wouldn't, right? I'll show you guys what I'm saying. So if our value is less than the head data, right? Then we know that our the node that we're going to create needs to be the new head. You see what I'm saying? If inserting an ascending order in a sorted list, and the value that we're trying to pass in is less than the current head, then we need to create our new node, and we need to say that the new node's next pointer is the current head, and then we need to um, essentially say head is equal to the new node. That makes sense to you guys? Okay. And I'll return this so it's a little more clear to you guys. So we're going to create our new node, and then we're going to say our new node next is equal to the head. We're going to set the head equal to new node, and then we're just going to return the head. So again, just breaking this down for you, we did our first base check. We've checked if the linked list is empty. If it's empty, we create our new node and we just return the head. All right. Check number 1 done. Check number 2. If we have a value that is less than the current head, we're still going to create a new node, and we're going to set the next pointer of our new node to be the head. And then we're going to set the head pointer to equal to the new node. And the reason why this works is because we already set our pointer of new node to be the previous head. That makes sense to you guys? If it doesn't, let me know and I can give me 1 second, guys. I'll show you okay. Da, da, da. I hate this. Okay, no. I know. This like is so weird though. Hmm. I have my iPad with me. Let me connect it and then I can do some drawings for you guys. Bear 1 second with me. I am so sorry, guys. If we need to, I can go a little bit further than the time. Okay. Mm, we'll just create a new random whiteboard. Okay. Oh yeah. Okay. Hold up. We're cooking. Okay, we're cooking. Okay. So we have this is the head, right? Let's say it has a value of 4. You guys can see? Perfect. Okay. And let's say we have our new node with a value of 2. Essentially, what we're doing, our pointer is going to point to the original head, and then we're going to change this head pointer to be the new node. So we still have the entirety of the original linked list just with the new node being the head. Is that better for you guys to see? Okay. I know pointers are really confusing. This helps you out. I get it. Okay. Alrighty. Now, this is where we get into a while loop, essentially. We're going to start traversing the list, right? Let's say I'm not even going to do circles anymore. Let's just do numbers. Let's say my new node is going to be 5, right? In my list, it obviously fits in between 4 and 6. So as I'm starting from my head, we're going to use a walker again, right? And we'll traverse our list, right? So we start at 2. Is 5 greater than or less than 2? It's greater than, right? So then we move temp. Now temp is at 4. Is 5 greater than or less than 4? It's greater than, right? But what's an important check? And I'll ask this for mm, you are correct, T. So it is going to be less than, but there's something important to see, right? If I need to insert 5 in between 4 and 6, what do I need to check? If I move temp to 6, can I go backwards? Right. So instead of checking the current node specifically, what do I need to check? Right, Ryan. You need to check the next. You need to check if the next pointer is greater than the new node, right? So we already see that we check if the value is less than the head. We have that tackled, so we don't need to worry about that, right? So what we need to do, I'm gonna call this cur, right? You'll see this a lot, and we can say while cur next is not null. That's important, right? We want to make sure that we're not going to go outside of the loop, right? And current next data is less than value. Or I'm sorry, I should say this. Mm, right. So this is an important check. So we have our walker, all right? So we're gonna call this her. It's gonna start at the head, all right? We're gonna check if the next pointer is null. We see that it's not. What's also important to check is the data less than the value that we're trying to insert. It is, right? Since both of those cases are successful and true, we move cur over and we do it again, right? So we look at the next pointer. Does it exist? It does. Perfect. Is it less than the value we're trying to insert? No, it's not. So then this fails. We end the while loop, right? Since we ended the while loop, this is where cur is at. We're trying to insert 5 into the list. So what do we have to do? We have to set new node next equal to cur next, right? So they're both going to point at 6. And then we're going to say cur next is equal to new node. So we'll get rid of this pointer and point it here. Yes. Yes. That's why it's important. Does this make sense to you, T? Okay. So if that being said, right, we've already traversed through the list. We found the node that is greater than our value, right? Um, I can just do this at the beginning, honestly. Let's just go ahead and create our new node and then, yeah. Sorry, guys. I'm just trying to make this better for you guys. Okay, there we go. Oh, my Atlanta. There we go. So we traversed through the list. We found the spot that we need to insert. We're setting new node next to be cur next. Remember when 4 was pointing to 6? We're going to point our new node to the 6. A while there's not really a difference. The only difference is like with if statements, like we don't know the exact size of the linked list. Like if you had a linked list struct and you kept the size of the list inside of there, yeah, you could use that to as like a incrementer to go through the list. But we don't have that. So a while loop would be like the best to use. But again, you could use an if statement as well. You could say like if cur next is not equal to no or something like that. You can do that too. Sorry if that confused you a little, but you can do either or. You just remember that while loops will continue to run until the condition fails. I guess that's the best way to put it. So until this fails, until this statement fails, we'll continuously do this. Your if statement will only run once unless you increment it somehow. That's the correct answer. I'm sorry. Okay, there we go. So again, we set the next pointer to be cur next, and then we take the current next pointer and we point it to the new node, and then we just return the head, right? The head is our entrance to the linked list. And that's how you insert an assorted linked list, right? So we tackled the base cases, we tackled if it was empty, we tackled if the head was less than if the head, I'm sorry, if the head was greater than the value we're trying to put in, obviously that has to be the new head. And we tackled having to insert it somewhere inside of the list. Okay. Does anybody have any questions in that regard? Do you need me to draw you guys the pictures for the insert at head? Would that help you guys again or anything like that? Okay. All right. Uh, Same. Okay. Insert beginning, middle, end. Okay. Oh, that's something I didn't. Well, this kind of handles it. Um, I'll just draw this for you guys. So, middle, end, delete by value, freeing the entire list, sorted insertion, list copying, tracing linked list modifications. Okay. Oh, this is important. I'm gonna handle these two for you by drawing some pictures and asking some questions, okay? Let's say I needed to free a linked list. What is something you don't do? What is the one thing you shouldn't do, I should say? Like right out the gate. Well, it's not really a for loop that's the issue, but Nicole got on it. You don't want to free the head immediately. Do you know why you don't want to free the head immediately? It's kind of something I've been touching on. Right, right. You lose the whole thing. Perfect. So, if that being said, what you would have to do, um, you would essentially have to do like a while loop and continuously loop through the list until you see like the next pointer is null. And to my understanding, like you would have to like recursively call it, if that makes sense. Right. So like you would have like your temp pointer to the head, you traverse, you'd free, right? Now this is null. Then you'd um start at the head again and traverse and then free. And now this is null. And then start at the head again and traverse. And then this will become null. And then you'd have like your base case where like, all right, well, we see that head next is null, then we could just free the head. That guys make sense to you? Yeah, we'll go through it. This wants us to create a next E as well. Hmm. I'm kind of curious to see. I'm kind of curious. Okay, so we have two pointers, head next. Temp is not null. Next, step next. Yeah, I can. I can. Okay, so we have the temp as head. Next is equal to temp next. We're gonna free temp, and then temp is equal to next. Oh, okay. This is another way to do it. That's interesting. So essentially, what this is saying is if we start here and this is temp, right? We see that is not null. This is going to be our next. We're going to free temp, and then we're going to set temp equal to where next is at. And then that iteration of the loop finishes, and then we're going to start all over again, right? So we're going to move next over. We'll free temp again, move temp here, move next, free temp, put temp here. Let's say this is null. We'll point next here, free temp again. We see that temp is null, and we end the loop. Right. I was thinking recursively, but this is another way to do it as well with two pointers. Is this easier for you guys? I know like recursion is something like it's something that I'm still not like masterful of. So this is probably better for you guys, the two pointer approach. If you need me to explain it in a different way, I can. Please let me know if you need me to. Okay, without the node next. Without the node next. Okay. Okay, without the node next. We're gonna do it recursively. And what we're gonna do is we're gonna check if the current node, essentially we're gonna start at the head. If it is null, we're gonna do nothing. That's our base case, right? So we're gonna have our base case, and essentially that's if the head is null, we're just gonna return, right? That's our base case. Everybody knows in a recursive function, your base case is how you terminate the recursive call. Okay. And then what we're do. Uh, okay. So we have our base case. We check if the head is null. If it is, we return. If head is not empty, we're gonna free head next, right? Do you guys understand what that's doing? So if this was our if this was our linked list, and we pass in 1 into our function call, um, we know we would check the base case. If it's null, it's obviously not null. So then we move down. We have a recursive checks. The recursive calls, I'm sorry. The first call is that we're going to free what's next, right? So then we're going to call um, the free function on 2, right? Because 2 is going to be the head that we're passing in. Okay. Same base case check. Is 2 null? No, it's not. So then we move down and we're going to free what's after 2. What's after 2? That's 3, right? Check your base case. Is it null? No. So then we free what's after 3. 4. Base case fails. We're going to free what's next. 5. Okay. And then recursive call again. Since 5 was the tail, we know that what's next is null. Wait a minute. We had the base case, right? So we start returning. So we return. Now we free the head, right? So we saw that this was null. We return back. We're freeing the head. So 5 becomes null. That finishes out. Then we go back here. We free the next. Now we free the head. This becomes null. And then we return back into this function call. We free the head again. This becomes null. We return back. We free the head again. This becomes null. We return back to the original call. This becomes null. And that's the end of our recursive call. Exactly. That's a good way of thinking it. That makes sense for you guys? Perfect. So that's how you free a linked list recursively. What if I wanted to remove a node by its value, right? Let's say I wanted to remove 4. What would I check? It's kind of similar to the insert sorted. You remember you want to remove it, so you need to have access to the previous one. Right, exactly. If temp next is equal to value, right? So we start at the head. I'm gonna call this cur. We're gonna check if cur next is the value. It's not, so then we can move cur. We're gonna check if cur next is the value. We see that it is, right? So then we call this temp. We change cur next to point to what's after temp, and then we free temp. You understand? So if we wanted to remove 4, you want to check if the next value is your target, because you have to reassign the pointer before it to what points after the target. That way you don't lose what's after that. Exactly. Exactly. That's right, Ryan. So if 4 was our target, You would reach two, you would see that cur next is equal to our target, aka 4, right? You would say um, node pointer temp is equal to cur next. Then you would say cur next is equal to temp next. And then you would free temp. Do you understand it that way, Nicole? Right? So we see that cur next is 4, which is our target. We create a pointer to that, an external pointer to the target, so we don't lose track of it. After that, we set the cur's next pointer to what's after our target, so we don't lose. Like, let's say there was more to this, so we don't lose this portion of the linked list. Then we free this, we free temp, and then this next pointer connects to what was after it. Could you use multiple next pointers from one node? You can create as many pointers as you want. It's up really up to you. I could see you using a two pointer approach to this as well. Like I could see you having like a cur and a next. You know what I mean? And then let me erase all this. I don't have enough space. Sorry. I can see you having like cur and next, and then you can do like while uh next data does not equal to target, right? Right, right, exactly. Like the more pointers you have, the more complicated it gets. Me personally, I like just checking just manually checking if like the next pointer to whatever, like having a single mover and just checking if the next is the target. And that way, like I only have to deal with two pointers at that point instead of, having two pointers and having to deal with a third, so to speak. Because like if we do this approach, right? And let's say we still wanted to remove this. We start cur here. Um, this is next. And then essentially like by this logic, right? While next data does not equal target, we would just move both of these over, right? So then this becomes cur, this becomes next. The data still doesn't equal the target. We move both pointers. This becomes cur, this becomes next. All right, we hit the case. Next equals our target. We have our cur. So what you do is that you say like cur next is equal to next. Um, and then you can just free next. Is that what you're getting towards, Levi? Where does temp get assigned to 4? Um, so I created that pointer. So I'll show you. Let me code it out for you. Maybe that's easier for you to see. We're passing ahead, and I call it the target, right? Obviously, you want to check if it's null, just return, and I'll show you my approach. Actually, no, this is cur. Okay. Oh my goodness. Stop with the auto typing, please. Okay. So I created my walker, right? And while the next element exists, and while the data does not equal my target, I move my walker, right? So if I get out of this, there's two possibilities. Um, the first possibility is that we went through the entirety of the list and it's not in there. I'm saying like actually accessing the next pointer from the next pointer within the node. Accessing the next pointer. Oh, I think I see what you're saying. So like you can do this, right? You can do that, right, Levi? You can do this. You can um if you're comfortable with that, more power to you. You can go as far out as you want. You can even access the data of that one if you wanted to, if that makes sense to you. But personally, I don't think you really have like a way. Like, let's say you started from the head and you just kept on going next until you reached your target. How do you assign the one before it to point to what's after it? Remember, like you're dealing with pointers. So at some point you have to free that target. So you have to create a pointer to that target, right? So like you could say like, yeah. Okay, is it clicking for you now? All right, perfect. So, all right, perfect. So as I was saying earlier, is that there's two things. Either one, you traverse through the entire list and it's not in there. So you would just return if you traverse through the whole list. If not, you would create this temp pointer that I was telling you about, right? So essentially we see that the cur next is the target. So then we create the temp to equal cur next, and then we set cur next to be what's see this is doing what you were saying, right? The cur next. You can do that, or you can say uh temp next, whichever one makes more sense to you, whichever way you can remember it. Just remember you need to point what's after the target, whichever one you want to do. You can do double nexus, or you can do what I did, create the pointer to that, and then point to what's after that pointer, whichever way. And then after that, you free your target. That makes sense to you guys? You guys understood that? All right, perfect. You would still need a helper to know which one to free, correct? Helper in which way? Like a helper function or like a walker? This is my only function. Oh. Yes, yes. You will always need to assign it to something because actually no, not necessarily. That's not necessarily. If you did it the way that he was thinking, like you can do this, right? So let's say Kerr is still the head. You can say while Kerr next next does not equal null and current next data does not equal to target. Cur is equal to cur next, right? And then you can say um cur next um next is equal to cur next next and then um so you're looking to past. Yes, yeah. You see, this is where it can get confusing and a little cumbersome. That's why I don't really recommend it. Yeah. So like essentially like you would look two ahead of it, and if the second one is like the target, then you can point to like after that, or you would point after that and then well, not point after that. You would free it and then point after that. But it's very cumbersome and it can get confusing and you can make a mistake. That's why I recommend this approach. Use a walker and that way you know for sure like you either went out of bounds or you hit it and you just create the temp and you free it. Okay. Any questions in regards to linked list? I think I hit all of these besides how to reverse it. Okay, we're good. All right. Well, this already spit it out. Um, so this is a three-pointer approach. So you would have our previous pointer, no, except for circular. I don't remember her covering circular linked lists, to be honest. Maybe that's just when the tail points to the head. Yeah. Okay. Yeah, I was correct. Yeah. Okay. That's essentially what a circular linked list is. Um, Gosh, give me my eraser. So in a circular linked list, there is no null pointer for the tail. You just point back to the head. Okay. So this is a normal linked list. This is a circular linked list. Um, Obviously, I think you would always have your head. That way you know where like the beginning of your function is, and then or the beginning of your list is. You would obviously use a walker to traverse the list for you, and then it would just loop back around. Like it would just be a never ending linked list, so to speak. everything we've been practicing, like how to move through linked list, etc., would still work. The only thing is like you wouldn't have to check if next equals to null. Does that make sense for you guys? I think the circular is just mainly for the queue. I don't really know why she brought up like circular linked lists because, like I said, I don't directly remember her ever covering that topic in class. She did it one time. Maybe I know I wasn't there like last Friday. That's probably when she did it or something. The only thing to be careful with circular linked list is since there is no like null terminator like at the end, no null pointer at the end, you could end up in an infinite loop. You know what I mean? Like if you're looking for a specific node or something like that, you could end up at like just infinitely going through like, and let's say you're looking for five and this was the head and you created a curve variable and you're just looping through, and obviously this points back, and you're just using a while loop. I don't even know why I just did that. Oh my goodness. And you're just using a while loop, like you would just infinitely go through the list over and over and over again looking for this five, even though it doesn't exist. You know what I mean? So what I would do personally, if I was looking for a certain value in a circular linked list, I would have a um case of like if head um does not equal to the target. I don't even know I did that there. Then you would say like cur is equal to head next, right? Like you would set it here instead, right? And then as you loop through, right? Um, as you loop through, you'd end up at four, and then if you reach this again, if cur is equal to head, you just return because you know that you've gone through the whole list. Does that make sense to you guys? Like obviously you would have to do some loop, you know, um like for me, I would do a while loop. Like I would say, so like we did this, like if head does not equal to target, then obviously um we'll create our cur, and then while cur does not equal target, or I should say while cur does not equal null, um and then we'll do if cur is equal to head, we'll return. If not, we'll just do cur next. That makes sense to you guys in the while loop. So you just check if it's null. If it's not, then you're gonna check if it's equal to the head. If it's equal to the head, you break free. If not, you move forward. Obviously, you do another check to see if it's equal to your target. If not, you keep on going through. I hope that makes sense to you guys. Okay. I know linked list is such a bulky topic in this. Okay. Um, is 10:20. Okay, guys. I only have about maybe 10 to 15 minutes. I'm so sorry. What is the last thing you guys want me to cover before I have to end it for the night? I'll be going to campus early tomorrow. So if you guys want to meet me at the library or something like that, I definitely can. Okay, I have one Q and one algorithm analysis. We can do a vote, or I can do one of each. What would you guys like? One of each. Okay. Tony, when you said algorithm analysis, are you guys talking about like finding O of N, or are you guys talking about like the runtime analysis where it's like T of N of something? You remember the thing that she showed us last Wednesday, like when she said it was being added on last minute? That thing? Okay. Perfect. I got a perfect example for that. Um, let's say we have a function that runs at O of 9 times 9 factorial. All right. And for an input size of 5, it took, let's say, 100 seconds. How long would it take for 10? Let's say 11. Okay. So we know that the function t of n is some constant times f of x. And as we remember today, f of x is basically our O of n, right? So in this example that I wrote down, we know that our O of n is this right here. We were given an example of what t of n is, and we know what our input size was, 5, right? Oh my goodness. Okay. So we know, so t of 5, right, which was 100 seconds, is equal to some constant times 9 times 9 factorial, right? What would be your first instinct to do with this? Do you guys know what factorials are? Okay. Yeah, 9 times 8 times 7, etc. Perfect. So what would be your first instinct to do? Right, Ryan. Right. So we would divide both sides by oh my goodness, 9 times 9 factorial. Gets rid of this, and we have our c, right? So then what we can do is for t of 11, we have our c now, right? It's 100 over 9 times 9 factorial. of our new, I should say, it should be called n factorial. I'm sorry. And our input size was 11 or 9. I apologize for those keeping up. 11 times 11 factorial. All right. You see what I did here, guys? I'm so sorry for jacking up the word questions. I'm just remembering this from the SI session earlier this week. Does that make sense to you guys right there, how I set it up? Okay. So from here, we would do e of 11 is equal to 100 over 9 times 9 factorial. And as we said, a factorial is just a number multiplied by the number one less than it, right? So we would have 11 times 11 times 10 times 9 factorial, right? Wait a minute. We can cancel out the 9 factorial. Did I select it? Okay. That leaves us with 100 over 9 times 11 times 11 times 10. I don't have a calculator on me, but you would essentially just do the multiplication, and that's what your T of 11 would be. Okay. She said that the numbers won't be as large, that will be easily able, to mentally calculate it, etc. This is just an example of like how to break down the problem and how to solve it. You know what I mean? And I know this is something that she didn't go over in class. I just thought it would be nice for you to see like how to handle factorials and stuff. Right, right. When I saw that, it really helped me out. So I just wanted to show you guys. Right. So all you need to remember is this formula right here. T of n is equal to some constant times f of x. And f of x is basically the runtime of the function. You just have to be able to pick the pieces of information in the word problem and plug it in. You're Every problem that I've noticed, you're solving for C. And then once you solve for C, you're plugging in the new input and finding out how much time it took for for that function to run with that input size. O of n is not input size. O of n is basically like how the function runs, um like what's the behavior of it. Yes, yes. Your n, your n is the input size. Okay. And then your t of n is how long it took. And then one thing I noticed with that factorial problem when I saw it was that our answer, or we were given milliseconds and it asked for the answer in seconds. She even said that today to be very careful when you're reading the word problems what they're asking for, because you can be given 1 unit and it wants you to convert it at the end for the final result. Just remember that, guys. Remember, you have 1,000 milliseconds in 1 second. I know, I know. I feel you, T. That's just something important to remember. Read the problems very carefully. All right, so that is algorithm analysis, or I should say empirical runtime analysis was mainly what he was trying to get at. And then the other one you guys wanted me to tackle before we called it quits for the night was cues, right? Or is there something specific you wanted me to handle with cues? Tell you what, I'll show you how to code it. Yeah, I can. I can. Oh my goodness. Oh, I gotta type it up here. It should be a node pointer. What am I doing? That's mainly all we should need. I know, I know. She kind of went like a mini review on Wednesday, but um, I have a bad feeling that a bulk of the test is going to be like those earlier topics that we covered and not so much like heavy on like stacks and queues. Like we might have like one or two problems, but I have a bad feeling it's going to be like um flood fill permutation type stuff. That's my big fear. Um, okay. So we know that queues are just linked lists, or there's two approaches. You have the array based and you have the linked list approach. For the linked list, it's really kind of easy. If you have a front and a rear pointer, remember that let me write it out for you. If we're NQing, we're adding to the rear. Oh my goodness. DQing, removing from the front. So that's when it's nice to have a front and a rear pointer. I imagine that they'll give us the struct for the queue if we're using a linked list approach. If you have a front and a rear, that's really nice. Remember, if you have both pointers, it's going to be a O of one runtime to NQ and DQ, right? Because if you're NQing, you can just create your new node and then, ooh, somebody type, yikes. You can create your new node, right? Let's just say it's -1, and then point it towards front, and then make front your new node, right? Just like a linked list, you're just updating the head, right? Or AKA your front. Um, if you're doing something to the front, sorry. If we're removing from the front, right, with our DQ, we can just um in the linked list approach, we're gonna free it, right? So we can just call this temp and then move front over here and then free temp. That's it. She didn't talk about it in class today. Um, she talked about flood fill like week 3, I think, or something like that. It's been a while. That's why I was saying like I fear that's going to be like some of the heavy stuff on the midterm. Um, and then the NQ, if you have a rear pointer, obviously you can just jump straight to the rear. You would have your new node. Let's say it's 5. You point rear to this, and then you'll just call this the new rear. That's it. That's NQing. And then this is DQing. NQ. That makes sense to you guys? That's all that is to queues in a linked list. Only NQ from the start. Correct. I'm sorry. No. Fabrizio, I'm so sorry. When you NQ, you're NQing at the rear, you're DQing from the front. Remember, it's first in, first out, right? So let's say we're building our list. There's nothing. We want to NQ1. So then our list is 1. We want to NQ2. So now we have 1, 2, NQ3, 1, 2, 3. We're going to DQ. So now our list is 2, 3. DQ again. Now we just have 3. Let's say we want to NQ 1. Now it's 3, 1. DQ. Now we just have 1. That makes sense to you? I'm sorry. I'm just short writing it, but you can write like the whole queue. You just write whatever they explicitly ask for. Right, exactly. Right. It's a queue, right? So if you're going to a restaurant and there's a couple of people in front of you getting checked in to get seated, it's the person ahead of you gets served first and you're in the rear. Or if you're in a grocery store, you're at Publix or Trader Joe's or whatever, you're waiting to get checked out. Perfect. Um, so the array approach, I'll cover that. I know I said I only had 10, 15 minutes. I just don't want to leave you guys empty-handed. In the array approach, because this might pop up in a um linear queue, right? Linear meaning like you're just moving forward, you're not moving back or anything like that. Jose, I have a fear that the circular queue is gonna pop up. I have a bad fear. I mean, she kept on talking about it. T, I heard it wasn't just her. Like I heard Guha was covering things today as well. Like just dropped it on them that was gonna be on the midterm. Um, so in an array, you would keep hold of the indexes of front and rear, right? So remember if the array was empty and you NQ, say we NQ1, we know this is the front and it's currently the rear. If we're going to NQ again, say we're going to NQ2, I'm not going to write it anymore. Then this becomes 2 and this becomes the rear. And then we're going to NQ3. Remember the front stays the same and we just move the rear. And let's say we DQ, we don't free anything. We just move the index of where front is. So remember, like if we had like the Q array, like you would essentially like return Q front plus plus. That's essentially what it's doing. Like if the front was here and inside of your NQ function, this is what you were returning. Essentially what you're doing is you're returning one and then you're moving front to the next index. Okay. Um, and then let's keep on going. Let's NQ again. We four, we NQ again, five, and remember the rear pointer is moving each time. Let's NQ again. Six, the rear moves here. If we try to NQ one more time, we can't, right? Because now we're outside of the array. That's out of bounds. So that's the limitation of a linear queue, right? You can't just continuously enqueuing because you'll fast run out of you'll run out of indexes in an array pretty quickly. So then that's when we have the circular queue. Oh my gosh, give me my eraser. Okay. And then this is where realloc comes in into play, guys. So I should make this smaller to give you guys a better example. One, two, three, four. Perfect. So this is where we have just the front, and instead of holding a rear pointer, we have a member of the queue called number of elements. You guys remember that? And then we also have um, size of the array. So we have the front index, we have an integer called num elements that tells us how many elements in the queue is currently active, and then we have integer of size of array, right? So uh let's say this was the front, this was the rear, and let's say this. I wanted to NQ again. Do you guys remember the formula? It was on the last quiz. Do you guys remember the formula for NQing in circularly linked list, not linked list, circular queue in the array? What is it you're checking for? Okay. So with these members, remember this is all within um the queue struct. You also have the array, right? What you would do is essentially you would say like queue um if you're dealing with a pointer like array and then brackets um you're checking you're doing the front um so sorry, it's the front index, right? Because it's the index plus the num elements. So these two together divided by the size of the array, but not divided by its modulus. Sorry. Remember, because you're gonna get the remainder of that division, And that remainder is going to tell you what index in the array it needs to be in. So, for instance, we have 1, 2, 3, 4, 5 spots in this array. We know that our front is at index 3. We have 2 elements, so that's 5. And then we're going to mod it by 5. So 5 divided by 5, what's the remainder of that? 0, right? Is index 0 available? Can I fill that spot? Yeah, I can. Remember, you can always overwrite. So I guess this should be the better example. This will be the better example. Let me do this to you guys. If this is the rear, right? So we do this. It's 3, and then 1, 2, 3, 4, 5. We have 5 elements divided by 5, right? 3 plus 5, that's 8. We have a remainder 3. Um, Obviously, all the spaces are taken. In the circular, so in the circular approach, correct. I was thinking about the linear approach, like you would just override it or whatever. Is front of the position in the array rather than what's in the spot. Correct. Front is just the index. It's not the element itself. It's just the index. Like if I wanted to access, like I would say like um that would give me this. Like if Q struct was a pointer, that would give me that 4. You see what I mean? But inside of the Q struct, I'm keeping track of the index of front, not what's actually in the front. You guys understand that point? It's very important. Okay, perfect. So when you NQ in a circular queue in the array, right? Obviously, you would check if num elements is equal to size of array. If it's equal to the size of the array, that tells us that there's no more space, right? So there's no more space. That's when we have to do the reallocation, right? So back into our DMA process. You remember from earlier, our DMA practice of the realloc. So you would have array equals realloc. This thing, I'm just gonna point it because I don't want to type it out or write it out again. That thing, and then you would have size of. We're just keeping it as integers right now, and then remember we have size of array, so it'll be this thing here times 2. You guys understand that? So when you check if the number of elements, remember the number of elements tells us how many active elements we have in the queue. You have 2 integers inside of that struct. You have the size of the array and how many members are inside the queue. Two different things. If those things are equal, then your queue is full. You need to reallocate for memory and you can just double it. You guys understand that? That makes sense to you? All right, perfect. Now, there's an important thing to do after you reallocate. So remember, if I were, I remember she did this as example. So if you don't remember, that's fine. If I were to reallocate, right? I had 5 in here originally. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's 10 right there. If I wanted to NQ, let's say I want to NQ 7. My front index is still 3. My rear is here. So I'm not holding rear. My number of elements is 5. My new size is 10. We have 8 mod 10. What's 8 divided by 10? What's the remainder of that? 2, right? So at index 2, can I insert? Oh, sorry. That's index. This is index 2. This is 3. Apologize. So there's something at index 2, right? So if this is my front, we keep a hold of the front index. After you reallocate, before you NQ, you need to move this stuff after the front. I apologize, Allison, when I said that you could overwrite in the circular queue. You cannot. You either DQ, um, which like you would set it to like 0 or something like that, or if the array is full, you would reallocate and then do this portion. You would move everything over. So then your new array, after you reallocate, would look like this. You would have 5, 6, 2, 1, 4. And then if I wanted to NQ, I think I wrote 7 or something like that. Right. So this is still my front. Right. So we have 3 plus 5 mod 10. We said that the remainder was 2. Um, boom. It will go there. You see? So you just got to be careful. You have to remember to move everything past the front. So after you reallocate, that's what you have to do. You have to move the elements past the front. Let me I'll find you the exact code snippet that she has posted. I was watching it earlier. I was watching some things earlier. Where are the cues? Where are the cues? Bam. We'll open this up fully. Okay. Where are the functions at? Where are the functions? NQ. All right. Where does he handle the case where he needs to? Does he not do it? Oh, okay, he does. So this is what I was saying earlier. So he checks if the number of elements is not equal to the size of the array. If it's not equal to the size of the array, then he knows that he needs to do the front plus the number of elements mod the size is equal to the new index of where we need to insert, and then we increase the number of elements. Okay. If it is full, this is where he does the reallocation. Why is he calling it elements? Is that what his struct is? Q, that's his array. Okay, perfect. So he's calling his array his Q array elements. Keep that in mind. So when you see elements, that's the array. And then we'll come back here. It's probably too small for you guys. Is that better for you guys? I apologize if you couldn't read it before. Can you guys see that now? Perfect. Okay, so just repeating what I said earlier. Sorry if it was too small, but when he's enqueuing, this is his enqueue function. He's passing in the array pointer and he's passing in the value that he wants to add. Um, he is checking if the number of elements is not equal to the size of the array. So he knows that there's space on the array to add something. So then he accesses the array. And then at this index, he doesn't do like he doesn't create the index and then add the value. He's doing it exactly in the brackets. So he's saying at the elements array, bracket, and then he's doing his math to find the index where the value is going to be inserted. So in parentheses, he's putting the front index plus the number of elements mod the queue size, right? So that will give us the index to insert at. He's setting it equal to the value he wants to pass in. He wants to enqueue. That makes sense? Okay. So that's if there's space on the queue. If there's not space, this is where we must reallocate memory and double the array. Okay. So he's allocating more space here. There we go. There's that realloc. So he has the array. He has the realloc. He's passing the array in again. That's the syntax for realloc. And then he's saying the queue size. And we're just, remember, it's of type int. And he's doubling it. Okay. And this is what I was talking about before. So he's copying all the items that are before the front index and copying them in their new correct locations. So he's iterating it through. So from I 0, so from the first index of the array all the way up to right before the front. So he's finishing right before the front. He is doing I. So like let's say we start at index 0, so 0 plus the queue size, right? So let's say our queue size was 5. Um, he hasn't increased it yet. So what I mean by increased it, he hasn't increased queue size here. Like if our queue size was 5, even though he's doubled the array, it's still 5 in the struct. Let me show you what I mean. Let me write that out for you. So size 5, right? Right. There's 10 indexes or indices, I should say. The size of array is still equal to 5 when he's doing this right here. Okay? You guys understand that? So he's doing so for instance, let's say we're at the first index, index 0. Our original queue size is 5. So 0 plus 5 is 5. He's setting that element that's there to the new index he just created, right? That's what he's doing here. So he's accessing that new index and he's passing in the original value. After he finishes changing the positions of those values, he's going to add in that new element, and then he's going to double the queue size in that struct. That way, whenever we do NQs back up here, we have the proper values. And then he's also increasing num of elements. I'm sorry if that's very confusing. If you need me to explain it again, let me know. I can even draw it out for you so you can see. Okay, I'll draw it out. Of course, of course. Let me make this full screen for you guys. Okay, perfect. So let's say this is our front. We want to NQ6. We see that num elements is equal to the array size. This is just pseudocode. I'm so sorry, guys. So we need to reallocate memory. We're going to double it. Okay. So this is still our front. So in that code, he was saying, right, he was iterating from index 0 to front minus 1. So if front is index 2, right? So 2 minus 1 is equal to 1. So he's going from here, from 0 to 1. Don't cry, Allison. I hope this is helping you guys. Do you see where I'm going with this? Please let me know if you guys are getting this portion. Like even if our front was here at index 3, we'd have 3 minus 1 is 2, and we'd start at the first index of 0 all the way to before the front. Does that make sense to you guys? Okay. Remember that the array size at this current moment is still 5. It's still 5. We have not updated that inside of our struct yet. So as we iterate through, we're going to start at index 0, right? So we have array is going to be this, right? So we're going to have I plus array size is equal to array I. Do you see what that's doing there? So if we're at 0, we have 0 plus 5 is equal to 5, right? This is 4, this is 5. So at 0, we have 1, so we put that there. Okay, we move on to 2, or we move on to 1, I'm sorry. 1 plus 5 is 6. So then at 6, we look at index 1, that's 2. We move that there. Meanwhile, that gets taken out, I believe. You see, is clicking for you now, Nicole? Perfect. After we do that, right? So then we do 2 plus 5 is equal to 7. Right, we move that there. I believe that gets taken out. After we make the move, right? The things before the front have moved to their new locations. That is when we can update this array size to the new size that it's actually supposed to be. It's all good. It's all good. Okay. So after you double the size, that is when you enqueue your new element. So let's say we're gonna enqueue 10, right? And then obviously you would do like num elements. So our num elements have not changed just yet. Our front is at index 3 plus our number of elements 1, 2, 3, 4, 5. We have 10 spaces, so mod 10, 8 mod 10. That's equal to 2. 2 is available. You can add in 10. And then after we have that successful NQ, we plus num elements, we increase it, and then we continue on. That makes sense? I know, I know. Just all you have to remember, front plus num elements mod size. That's the formula. Yeah. And then I believe if you wanted to DQ in a circular queue, it was like front plus 1 mod size, if I'm not mistaken. I'm pretty sure. Let me double check that. DQ, DQ. Bam. Look at that. Somebody call Google. They get hired. So in a circular queue, um, we're gonna check if it's not empty. We're gonna capture the value that we need to return, and then we're gonna adjust the front, right? So it's front plus 1 mod the size. It's essentially gonna do what we've been doing is just moving that front index just by 1. It's just that you're moving it accordingly to the size of the array. And then you're dequeuing, I'm sorry, you're de-incrementing num of elements and then returning the value. Okay. Does the array approach to queues make sense to you guys a little bit more now? All right. Okay. Um, I can shoot for 8:30 to 9 in the morning to meet at the library. How does that sound for you guys? I live in Ocala, so it takes me like an hour and a half to get to campus. I know it's tragic. RIP. Yes, an hour and a half. I chose UCF over UF. Of course, of course. I will figure out where to upload this and then I'll shoot it in the Discord and the other chat for everybody else as well. All right, you guys have a good night. Um, don't try to overstudy. Um, in the morning, I plan on going over the flip fill and permutations for whoever wants to meet with me. I'd recommend you guys to look over that. But you guys have a good night and stay safe out there, guys.